Having done the harmonic oscillator, what, 3 times already? Twice? I've lost count. Let's do the harmonic oscillator equation again. Are we all up for that? Yeah. It's exciting times, what can I tell you? But now I'm going to write it one more different way. We'll go back to y, keep time. This is a common way for the equation to show up in physics. Why? Anyone have a guess? Say b equals 0. What did I just obviously write?
Just
straight up harmonic oscillator with omega naught equals the square root of k over m. Right? The omega naught squared gives me the right dimensions because I have a 1 over t squared, which is the dimensions of 1 over time squared. A frequency squared is a 1 over time squared. So I've explicitly made the dimensions right now physically. So I'm really moving into a more physical representation of the equation. And omega naught squared is going to be that characteristic frequency for my equation. The b is the damping parameter. The 2 turns out to make some of the math later look nice. So that's why the 2 is there. Now, if I want to just very quickly, let me put it this way. So now, given that I have a driving, there's really 2 choices we have. There is the case we just did, where we're worried about sort of infinite space, and I'll take the Fourier transform of G. There also is a case where G of t is periodic over some domain. And then I'm going to be more likely to use the Fourier series. And I'll show a little more detail what we mean by omega sub n in a moment. So really, which technique, which idea, why we have both Fourier series and Fourier transforms, again comes down, this is I'm operating over the whole band from minus infinity to infinity. And the function doesn't even really have to be periodic. It can be any function. This works best if I have a periodic function over some period that I'm going to work on. This one we just did. I just want to remind you, if I use this new notation, the answer will come out in kind of a more standard form. Where I have omega naught squared minus omega squared plus 2i omega b. And if you notice, this is more standard because, for instance, if b equals 0, I immediately see what sort of behavior. If b equals 0, what happens to this function at a certain place? When omega equals omega naught, it becomes undefined. What do we call this? When something becomes really big? Resonance, right? So if I hit something with the natural frequency. So how many of you have ever swung on a swing? And can you actually get yourself going without someone pushing you? Yeah. And what are you doing?
Matching up with the natural.
You're trying to match the natural frequency and develop a very large amplitude. There is, of course, some damping, so you don't go to an infinite amplitude. Right? And the damping is always in the physical system, even if it's incredibly small, and that keeps us from truly blowing up. But if you see any of those amazing videos of bridges falling apart just from the wind, because of like the Tacoma Narrows Bridge is a famous one, those are resonance effects, and we see it in the frequency response by looking in Fourier space. We good with that? Now, doing the Fourier series version is a little different. The first thing we recognize is that we plug in for the Fourier series on the right-hand time. So let's suppose we're doing periodic in the interval -1 to 1. So as we come up to our test on this stuff, you have to keep in mind that we need to define the region that we're periodic over, because that will set what we write for our function. And we get a 2 pi n times t, and this is what we mean by omega sub n in this case. Right? We just absorb the 2 pi and the n into one thing, and we call it omega sub n. Now, we would also want to normalize, and we would normally have a square root of 2 here. But again, with the differential equations, it's easier to just absorb the normalization into the amplitude. Because we'll see at the end it just drops out. Now, the Fourier transform, therefore, of y of t, the Fourier series, is a sum over n of y sub n e to the I omega nt. So I can take the Fourier series for y and plug it into my equation, and I will get minus omega n squared sum of n y sub n e to the I omega nt plus 2ib omega n sum over n y sub n e to the I omega nt plus omega naught squared times the sum, all of this equal to my sum over n c sub n e to the I omega nt. Now, why have I helped myself by doing this?
Now it's just algebra.
But what's sort of important about the algebra? How might I rewrite this in a way that would be very useful? Well, first of all, what can I do with my sum over n? Does it come outside of everything? Right? This is all linear, and they're all being summed over the same thing. So I really have a big sum over n, and I can actually just switch now to my repeated index notation. So that may help clarify the situation a little bit. And for this equation to be true, what does it have to be true as? That wasn't really a good English question. But this has to be true for what? Every single, what can I factor out now? I can certainly factor out the e to the I omega nt, because it's got to be true term by term. Right? It can't be true. It can't be that an e to the I omega 6 cancels an e to the I omega 3. They just don't do that. Okay? So we get to cancel our e to the I omega n's because it has to be true term by term. Another one of those big ideas that we've mentioned in the past. And now it truly is just algebra. And if you redo your algebra, you'll find y sub n equals c sub n over that. So what have we found here? If you were to then put this back into your Fourier series, are there certain terms that are going to be more important than other terms? Which ones?
The ones where Cn is big.
Well, no, Cn, yeah, if Cn was big, that does matter. But what will dominate more than if Cn is big? If this is really close to our resonant frequency, those are really going to dominate. Okay, so now if there is no driving at the resonant frequency, then what's going to determine this mostly is probably C of n, how big that is. Okay? And then again, we get our phase shifts here and a slight frequency shift. So we can now put this back together, plug it into our series, and get a solution. And notice, with Mathematica, life becomes even more powerful because we really can do these series quite easily. And we can really look at individual terms. And again, if you know your driving has a certain, like if your Fourier series was sine cubed x, for instance, how many frequencies are in there? 2. We did that last in the exercise. So there's insight to be gained by thinking about it in terms of the Fourier series if your driving term has only a few frequencies in it that are dominating. And that's one of the reasons you really want to figure out, for a given problem, which is the best math technique to use to attack it, because which is the math technique that gets to the physics I'm most interested in quickly. And a lot of modern signal processing and a lot of modern techniques for understanding data have to do with coming up with better basis vectors than just sines and cosines. So for instance, almost any compression algorithm for video or music is based on that frequency space may not be the best representation of your music in terms of the smallest amount of data. If there are other eigenvectors that capture the video or music better with less eigenvectors in the expansion, then I would use that basis, and all I have are the numbers that go, the amplitudes of those eigenvectors. That's all I have to keep track of, and then I can undo the compression. And what makes the compression lossy is if I don't use a complete set of eigenvectors. Right? I will lose some information because I won't capture all of the projections. And when I inverse it, something will get lost.